So electrons are extremely important for a variety of reasons, but obviously in biosynthesis, they tend to be more reduced than their building blocks. For example, lipids is a classic example. Lipids are very reduced. Well, how do we get these electrons? Obviously from the food, but how do they move around so that we can then put them on the things we need to synthesize? So it turns out that when we burn a lot of our food to make ATP, not all hydrogen and electrons end up to oxygen, okay? Directly. In fact, what happens to them is that in all cells, okay, the electrons and the hydrogen are transferred to NAD or NDP. Okay, so and now the oxidized NAD and NDP now becomes reduced with the hydrogen and electrons and becomes NADH and NADPH. How do they look like? We have some common themes here again. Okay, here is the adenine base, the ribose, phosphate, and then some extra stuff, um, which happens to be the business part of the molecule. Is this part here? This is where the electrons will come in. I do want to point out that we've seen now similarities with nucleotides, with the NAD here and NADP. Um, this module is found everywhere, and this is what is also found, let's say, in nucleic acids, especially RNA, and this is another indication of all these metabolites that are so important for all metabolism in all cells. Probably they reflect an early prebiotic RNA world. Okay, so we keep seeing them again and again. All right, so this is how NAD, in the oxidized form, how it looks like, and NADP for all redox properties is identical. The only difference is a phosphate here at the 2 position. It's phosphorylated compared to NAD, but since the business molecule is the same, all the redox parts are exactly the same. Okay? All the redox properties. So what happens? So that's just the business part. Okay, as I mentioned, the ribo and ADP is, we just write it up now. We don't show it. So again, all this part would be the ribo ADP part, and here we're dealing with just the business part of the molecule. So in all electron transfers with that involve NAD and NADP, the reactions are the same for NADP, but here what you see is for NAD, let's say. There are always protons that are involved. Okay, so the electrons actually move as hydrides. Okay, and the proton with the 2 electrons, that's a hydride. Okay, the proton with 2 electrons will attack this position. Okay, and the bonds will bounce. The electrons on the aromatic ring will bounce first here and then onto the nitrogen. And what you're going to end up having is NADH, the reduced form of NADH. Okay. And again, the reaction is exactly the same for NADP. So the key point here, NAD and NADP are the universal electron carriers in cells. And whenever you have electron movements involving NAD or NADP, the electrons move always as hydrides. So it's 1 proton plus 2 electrons, always go together. So let's go back to our scheme here, where we see the fundamental half cell reactions for all the oxidation states of carbon, from carboxyl, carbonyl to hydroxycarbon, and all the way reduced to hydrocarbon. We've discussed this before. These are the E values that you see here in millivolts for each one of these half cells. And where does NAD, what is the half reaction here for NAD to NADH? It fits right there. The E value is minus 320. So it can be used actually to couple some of these reactions. And what's important to realize here, shown here in this scheme, is that what's favorable, I showed you how to calculate the delta E value, which has to be positive to be favorable. What tends to happen is that the compounds that are rich already for electrons become richer, so they get even more reduced. So as long as you can couple something as a reduction, let's say, you pick something, the green one, if you couple this, you want to move it like this as a reduction, you have to couple it with something that's below it, so it's more negative, the E value. Then it will be favorable for the reasons that we described. If it's more negative, then you have the minus sign in the subtraction there, so it ends up being positive, so the overall thing becomes positive. So going from low, from negative E value to positive E value is more favorable, and the simplest way to describe it is that favorable reactions in these redox couplings, the electron-rich compounds tend to get richer. Okay? That's thermodynamically favorable. So, but there's something interesting that happens in cells. It's not 100% of the time, but in the vast majority of time, NAD and NADH mostly participates in oxidations. Now, as I told you, NAD and NADP, I mean, they're identical redox-wise, yet we find one, the NAD, the unphosphorylated version of it, to participate most of the time in oxidations, and we find the phosphorylated version 1, NADP, to participate in reductions. Okay, so NADPH tends to be oxidized itself. It participates in the reductions and is used in anabolic biosynthesis. When you want to make big things, you use NADPH. You don't use NADH for the most part. There are some exceptions. So why is that? I mean, redox-wise, they're the same. How does that happen? So the way the cells can achieve this sort of separation of use, if you wish, between NAD and NADPH is that they keep the relative concentrations very different. So there is a lot more NAD plus, okay, than NADH in the cells. So why is that important? So if you bring in electrons, let's say from food, you will favor the formation of the reduced form of NAD to NADH. Okay. So those electrons tend to find their way onto NAD and becoming NADH now. On the other hand, the cells maintain completely the reciprocal relation in the relative concentration of NADPH to NADP. So NADPH is found at much higher concentrations, so it's more favorable to actually use NADPH, okay, than generating it. Okay, so it goes with its gradient here in concentration. So mass action again favors transactions going from higher concentrations to lower ones. So it favors the reduction of NAD plus to NADH. So it favors the acceptance of electrons by NAD plus, which happens in catabolism for the most part. In anabolism, however, the mass action here, because you have these different concentrations, favors the use of NADPH. Okay. So again, we get back to this fundamental thing that we had seen before with the ratio of ATP to ADP. Even though it is so much more favorable to hydrolyze ATP and make ADP, yet cells maintain about 10 times more ATP than ADP. So about 1 billion-fold away from equilibrium. Again, here we also see that they maintain different concentrations of very similar compounds here, but to satisfy their purposes. So, which states in another way again that even though living things are in steady state, they are far, far from thermodynamic equilibrium. Which we're going to take a little detour here and discuss a point that has been raised. Is, I mean, somehow is life Maxwell's demon? Who pays for all this different, concentrations are far, far from equilibrium? So let's define Maxwell's demon here. How do you get to these situations far, far from equilibrium? You have two compounds, a blue and a red one, and you have two compartments A and B, and you start out, and the two compartments A and B can communicate freely. So, red stuff can go either way, and blue stuff the same thing. So they are sort of distributed equally in these two compartments when the door is open. But you have the little demon here, it's this green thing here, and there is a door at the opening. And the demon can be very choosy and can close the door or open the door exactly when it wants to, in a way that it opens the door only when a red one is ready to go from A to B, or a blue one from B to A. So in the end, by selectively opening and closing the door here, you end up with two very different distributions of A and B, so different concentrations in compartment A or B between the blue and the red balls, right? So is this how life is? So there is a little demon there that somehow moves little doors and keeps pushing things in different concentrations. Um, well, the demon is very smart here. It somehow it knows when to open the door, right? But how do cells know when to open the door? Um, well, they don't actually, but that information comes by being alive for billions of years. I mean, you are actually seeing the information cost. Okay, it costs a lot of energy, a lot of failed experiments, meaning dead organisms. Okay, over the billions and billions and billions of years that everything is evolving, and it's very costly. And the price has been paid. So we live off all those experiments, successful and failed ones. It takes a very long time to acquire that information. So no, life is not like the little demon. All right, so we're gonna now we've talked about reduced fuel. I keep talking about this for a while, and it has electrons, and let's try to organize all of biochemistry here. Everything we're going to talk about in one slide, right? Because we have some very important molecules that we've discussed. We have ATP and we have NAD and NADP. And if we take our fuel, which has a lot of they're bigger things and they have a lot of energy, and they have a lot of electrons. We break them down in reactions that we define them as catabolic. You start from something big and you break them down to something small, and that will generate oxidized products. So where did the electrons go? Well, what's the electron currency here? They went into these molecules, NADH and NADPH. Okay. And of course, we got from big molecules, we got to small oxidized, big reduced molecules. We end up with small oxidized molecules. Then what happens? We haven't seen ATP yet. Well, most of the ATP, as I said, we generated a little bit in catabolism, like in glycolysis, as we will see, but most of the ATP is made then by using these electrons that are now found on NADH. Remember, there's a lot more NAD plus than NADH, and this NADH now has all these electrons. It carries them to what? Eventually, these electrons will move through an electron transport chain and find their way onto oxygen when we respire. Okay, that's oxidative phosphorylation, and in the process, ions will move across some membranes, and we have a battery charging operation. And because of that difference in voltage, our molecular machine will be able to make, which we will define, ATP synthase, will be able to make ATP. So the flow of electrons from NADH to oxygen charges our battery, and then we can make ATP. And of course, in the process, as the electrons go away from NADH, you regenerate NAD+. So the whole thing can happen again. And the oxygen, of course, when we expire, it has been converted to water. So now we made ATP. Well, is that all? Well, what do we use it for? I mean, we can use it for anabolism. And in this case, we need energy, which comes from ATP, which we just saw how we got it. And we have some oxidized precursors, some small things. And we use the electrons that are now on an ATP, okay, to drive biosynthesis. So anabolism is biosynthesis. So energy, electrons, and small building blocks will get you to the exact large reduced products that you need to make your own cells. And of course, that's how you spend your ATP, and that's how you now reoxidize again here, and you have an ADP plus, and the whole thing goes again and again and again. Now, believe it or not, that actually summarizes all the reactions we're going to be talking about. If you know more or less, if you can pinpoint whether you lose ATP, what kind of electron source you have, you can figure out where you are. That's the organizing principle of all the reactions, and you see how everything gets coupled together with these very important molecules we were just discussing, the electron currency, and the energy currency, ATP and NADH and NADPH. Okay, and at this point we will stop this video. This concludes this video, and we'll continue next time with another video about the transport of small molecules in the cell.